All right, example 3. Why does r squared only range from 0 to 1? Well, I think it might be helpful here to start off with what r squared is. 1 minus the sum of squared error over the total sum of squared, over the total variance. Right? Now, let's think. Can SSE ever be greater than SS total? No, it can't. Because SST, by definition, it equals the sum of squares from regression and the sum of squared error, right? So this, by definition, has to be smaller than this. And none of these can be negative because they're squared, right? And so whenever you have 3 positive numbers, it is absolutely the case that if you add 2 positive numbers together to get another positive sum, that sum has to be greater than or equal to these, right? So either this is greater than each of these or it's equal to one of them, right? Because it could be like this is 0 and this is 100%, right? So there is just absolutely no way that this could be bigger than 1. No, right? I mean, so not bigger than 1, but bigger than SST? No, cannot be, cannot be. So this proportion has to range between 0 and 1, right? It's got to be smaller than, it's got to be 1 or smaller, right? Because they could be equal, so you could get 0. This could be 0, this could be 1, right? But there's no way that this could be bigger than this, right? So because this value only ranges from 0 to 1, 1 minus something that ranges from 0 to 1, this whole thing could only range from 0 to 1, right? And so because of that, r squared can only range from 0 to 1. All right, example 4. Now this is going to be a doozy. Find r squared for this set of data. Examine whether this is also r times r. So let's think about what we're going to have to do. We're going to have to find r times r. And so r is the correlation coefficient. And so that's the sum of the product of z-scores, z sub x times z sub y, and sort of the average product of z-scores, right? So we're going to have to find that, right? We're also going to have to find r squared, right? And in order to find r squared, that's 1 minus sum of squared error over sum of squared total. And in order to find this, we need y hat, right? And in order to find y hat, we need the regression line. Crap! We got to find the regression line, right? Now, to find the regression line, one thing we could do is once we find the correlation coefficient, we could use that in order to find B1. Right? Or obviously you could also just find B1 in other ways too. But this is one sort of shortcut. And then once we find B1, we could find the intercept, y minus b1 times x, right? Because we'll have a whole bunch of data. So we have all this data, but we're going to have to do a lot, right? So let's get started. If you go to your examples and go to example 4, here's our data. I'm just going to move this over to the side because we're not going to be needing it for a while. But we already can see that it's probably going to be a positive correlation, if anything. So let's just start by finding the correlation coefficient, because that's pretty easy for us to find. And once we have that, we could find other things. And in order to get started on that, it often helps to have the sum, the average, and the standard deviation. And I'm just going to make these all bolded and in red so we know that they're different. So I'm going to find the sum for these. You actually don't need the sum here, but I figure might as well. It's not too hard. Here's the average. And let's get the standard deviation, because we're going to need that for z-score anyway. Great. So we've got all that. Now let's find the z-scores for TV watching, and also the z-scores for junk food. And so it sort of makes sense, I guess, that there's this correlation, the more positive correlation. The more TV you watch per week, perhaps the more junk food calories are consumed. That's not altogether unbelievable. But let's see. Is the correlation strong? I don't know. In order to find the z-score, we need to have the TV watching data, right? And subtract from that the mean, right? And I want that distance not in terms of the raw distance, but in terms of standard deviations. How many standard deviations away? So all divided by standard deviation. And here I'm just going to lock down the row so that, you know, I always use the same mean and standard deviation. So I'm going to move that down a little bit. So once I have that, oh, I don't need that. Once I have that, I could just drag that all the way down. And while we're at it, why don't we drag it across? Oops. Oh, we forgot to find these for junk food calories. But once we have that, then we see this. So let's just double click on one of these and test it out. Let's see. It gives me the junk food calories minus the average over the standard deviation. Perfect. And let's just eyeball this data for a second. We see that roughly half of the z-scores are negative and roughly half are positive. And here too, roughly half are negative and roughly half are positive. So we know that we did a good job in finding z-scores. Now in order to find that the average product, we're going to need to find the product. So ZTV times the Z of junk food. This times this. And once we have all of that, now we could sum these, and we could find the average. So this divided by count, however many data points I've got, and then subtract 1. All right. So we found our average, and that's R, right? Just regular old R. Now, that R, it's 0.58. So it's not super duper weak, right? But it's not really strong either. It's sort of in the middle. Once we have that, we could find, so this is R, right? Just labeling it so that I know where it is when we come back. Now that we have R, we could find B1. B sub 1. And in order to find B sub 1, that's just going to be R times the ratio between the standard deviation for Y and the standard deviation for X. Thankfully, we have that right over here. So the standard deviation for Y divided by standard deviation of X, that proportion. And so we get B1 is 10.75. And once we have B1, we could find B sub 0. Because remember, we have the point of averages, but we also have all these points. You could substitute in any one of these points. any one of the points between x and predicted y. Actually, so yeah, you can't substitute these points. You have to substitute the point of averages. My bad. All right, so in order to get the point of averages, we want to get y minus b1 times x. And here we get b1, the intercept, b sub naught, or b sub 0, is 186. Great. Now that we have b1 and b0, we can now find predicted y, right? So let's go up here. And so I'm just going to, just to help us out, I'm just going to color these in so just some color, just so that we know that this one is all about finding the correlation coefficient, right? So we found the correlation coefficient. Now what we want to do is find r squared. And so in order to find r squared, let's think about what we need. We need predicted y, so predicted junk food, right? So predicted y, or junk food, right? And we could easily find that. And once we have that, we know we're going to need y minus predicted y squared. That's our error term, our sum of squared error. But we also are going to need y minus y bar squared, right? And that's going to give our total error. So let's start with predicted y. Predicted y is always going to be b sub naught plus the slope times x, which is TV watching. Right? And we want to lock down b sub naught and the slope, b sub 1, because we don't want those to move. Great. Once we have that, we could find y, junk food, oops, y, I just want the first one, y minus the predicted y, and all of that squared. Okay? And then finally, we want to find y. Oh, let me put a parenthesis there. Y minus the average y, and all of that squared. Oh, you can't see it. Here. But we want this average to be locked in place. We don't want it to move. Great. Okay. Once we have all three of those pieces, now we could just do the easy job of copying and pasting all the way down. Ta-da, right? Easy. And once we did that, we could sum these up because we're going to need to have the sum of squared residual. And we're going to need to have the sum of squared deviations from the mean. So in order to find the sum, I could just copy and paste that. So let me check. Yep. And so once we have the sum, I can now find r squared. So r squared, in order to find r squared, I can just put in 1 minus the error term, sum of squared error, over the total. Okay, let's see. And we get 0.3377. So the regression line accounts for about 34% of the total variation, right? And let's see, is this r times r, right? Is that going to be the same thing? Well, we have r, and we could, just square it. And voila, we get exactly 34%. So if you get a question like this, you know that it's going to be a long road ahead, but Excel can help, obviously.